Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. WED.
Glad to be here.
So imagine a water treatment plant, right? Like somewhere in Minnesota.
Okay.
The pumps are humming, the indicator screens on the HMI look perfectly green, and the overnight operators are just, sipping their coffee.
Right. Totally normal shift.
Exactly. But silently, beneath that interface, there's a script. And it's a script written by an artificial intelligence, a script that required absolutely zero knowledge of industrial engineering to create.
Wow.
And it is actively rewriting the fail-safe limits of a chemical mixing tank.
That is terrifying.
Yeah. So today we're looking at how the supposed air gap between digital code and physical destruction just completely vanished.
Yeah, we are breaking down a really critical joint advisory today. It's from CISA, the NSA, the FBI, the Department of Energy, and the EPA.
That is a lot of alphabet soup paying attention to one thing.
It really is.
Yeah.
And they are sounding the alarm on an active cyber threat that's targeting internet-exposed Siemens S7 series programmable logic controllers.
The PLCs.
Right, the PLCs.
Oh.
These are the embedded computers running the actual physical processes in, critical manufacturing, energy pipelines, water facilities, agriculture.
The stuff that keeps civilization running, basically.
Exactly. And just to set the stage impartially here, relying purely on the federal findings, we have a very specific background. Over the last several months, suspected Iran-linked operatives, groups that are often tracked as cyberattacks,
Right.
they have relentlessly targeted PLCs at water systems across multiple states, including that major disruption in Minnesota in late July.
Yeah, I remember reading about that.
But the advisory we are dissecting today, it does not formally attribute this specific new AI-assisted activity to a particular government or criminal group. We will not be speculating on the politics of it.
Right, no politics here.
We're simply analyzing the raw mechanisms of the threat exactly as laid out by the federal agencies.
Perfect. So our mission today is to really pull apart the technical gears of this attack, right? We need to weigh the operational consequences of how we actually respond on the factory floor and, force a realistic decision under extreme constraints.
Yeah.
Because I am approaching this strictly from the perspective of operational technology, OT.
The plant floor reality.
Exactly. My sole priorities are physical production, technical feasibility, and preserving validated, hard-coded safety logic. I frankly look at IT security solutions being thrown at delicate, time-sensitive industrial equipment with, profound skepticism.
Which is fair. But my perspective is anchored entirely in attacker risk. I am looking at the sheer velocity of AI adaptation here, the quality of the forensic evidence we are gathering, and ultimately the business impacts of a successful breach.
Right.
Because the threat landscape is moving exponentially faster than legacy industrial upgrade cycles. We either adapt our monitoring and mitigation strategies to match that velocity, or we're going to face catastrophic, uncontainable physical consequences.
Technical breakdown.
Well, let's get into the weeds then. So to understand what is really happening underneath, let's get into the technical breakdown.
Okay, so the central engine of this threat is an open source library. It's known as Python Snap 7.
Okay.
Attackers are taking this library, they're feeding it into AI coding assistants like GitHub Copilot or ChatGPT, and they're generating custom tools that perfectly mimic legitimate OT engineering software.
Wow. Okay, so it just acts like a real engineering workstation.
Exactly. This grants them the ability to read and write directly to the memory, the configuration data, and the ladder logic of these Siemens S7 PLCs. And they're doing it using the native S7 COM protocol.
Unpacking that library is critical because it explains why this specific campaign is accelerating right now. For decades, industrial protocols were, well, they were obscure, right?
Really obscure.
They were undocumented and really difficult to interface with unless you bought a $50,000 engineering workstation from the vendor.
Right, you had to have the proprietary gear. But if you track the development history of the Python Snap 7 project, version 3.0 represents a monumental architectural shift.
How so?
It was completely rewritten in pure Python.
Oh, wow.
Yeah. Prior to that release, the tool was simply a Python wrapper stretched over a C library called Snap 7.
And dealing with C libraries in an attack scenario is just miserable.
Oh, it's a nightmare.
Yeah, they require native dependencies, you got to compile them for specific hardware, and, managing different dynamic link libraries depending on the target OS. It's just a lot of friction.
It was a massive friction point for attackers.
Right.
A C library needs DLL files for Windows, SO files for Linux, dlib for a Mac environment.
Right.
So if an AI writes a payload relying on a C wrapper, the attacker still has to jump through all these significant compilation oops just to make it execute cleanly on whatever compromised jump box they happen to land on.
Which slows them down.
Exactly. But version 3.0 stripped every ounce of that friction away. Yeah. The entire S7 protocol stack, TPKT, COTP, and the S7 protocol itself, it is now implemented natively in pure Python.
So it just runs anywhere?
Anywhere. It runs seamlessly on Windows, Linux, OS X, ARM architecture, or even inside tiny little Alpine Linux containers, with absolutely zero native dependencies.
So the barrier to entry has essentially evaporated.
Completely.
Because AI coding assistants are extraordinarily proficient at writing pure Python. An attacker no longer needs to spend 6 months reading Siemens manuals to understand the complex intricacies of industrial control system packet structures.
Well, they don't have to understand the packets at all.
They simply instruct an AI to write a Python script leveraging Python Snap 7, tell it to connect to a target IP address, and read a specific data block. The AI handles all the syntax and the protocol formatting, and the pure Python library guarantees it executes anywhere.
Which is why attackers are capitalizing on that ease of use right now. They're feeding search queries into internet scanning engines like Senses and Zoomeye, and they're specifically hunting for PLCs with TCP port 102 exposed to the public internet.
The S7 COM port.
Exactly. And once they identify a target, they deploy these AI-generated Python scripts for initial access. And it gets worse. If you look at the development branch of this library, specifically version 4.0, we are seeing experimental features emerging.
Like what kind of features?
Things like a multivariable read optimizer and support for the S7 COM+ protocol.
Okay, S7 COM+.
Yeah, it's the modern cryptographic protocol required for communicating with newer S7 1200 and S7 1500 PLCs, especially when legacy communication methods are disabled. The fact that the open source community, and consequently the threat actors, are actively developing S7 COM+ support, it just indicates this threat is rapidly maturing.
Well, I'm going to challenge that framing right there regarding the severity of version 4.0.
Okay, why is that?
Because we need to ground this in engineering reality. Version 4.0 of this library is currently unreleased and highly experimental. S7 COM+ communication is only a requirement if the OT engineers actually complete their basic commissioning checklists and disable legacy communication.
Right, but...
No, listen, if a facility configures their S7 1200 or 1500 controller correctly, which literally means unchecking a single box in the TIA portal that says permit access with PWG communication from remote partner.
Okay, yeah, that one checkbox.
Yes, that one checkbox. If they uncheck that, these AI scripts, which predominantly rely on basic unencrypted S7 COM, will simply fail. The controller will flat out reject the connection handshake at the socket level.
Sure, if configured perfectly.
So complaining about attackers developing S7 COM+ tools is kind of like complaining that burglars are inventing a new master key when you left your front door wide open and the screen unlatched.
Okay, I hear you. But that assumes every facility operates with pristine modern configurations, which completely contradicts the physical evidence CISA is presenting right now. The federal advisory explicitly notes that this is an active threat resulting in real compromises today. Attackers do not need the unreleased version 4.0 to inflict massive damage right now. Target facilities are frequently running legacy hardware.
Like the older S7 300s.
Exactly, S7 300s and S7 400s that inherently rely on older protocols. Alternatively, they're running modern systems that were just poorly migrated. In countless critical infrastructure environments, PUGEP is enabled by default.
Yeah.
Or, an integrator flipped it on a decade ago to make a legacy HMI connection work, and they just never went back to secure it. That simple misconfiguration leaves the entire memory structure, the configuration data, and the ladder logic completely exposed to the internet.
Okay, I will qualify that the situation on the factory floor is often far from ideal. Legacy systems fundamentally rely on PTT for rapid, unauthenticated data exchanges between older PLCs or legacy human-machine interfaces.
Because it was easy to set up.
It was very easy, and engineers frequently leave it enabled on brand new system upgrades simply to ensure backward compatibility with older machinery on the line. Or, just to make spinning up a quick diagnostic connection during a midnight outage slightly faster.
Right.
It is a dangerous operational convenience, I'll give you that. And it does leave a gaping initial access vector.
Right. And the immediate consequence of that reality is that organizations must relentlessly audit port 102. Defenders have to restrict access to the TIA portal and Step 7 engineering software at the network level.
Yeah, segment the network.
You cannot allow any machine on the corporate network to arbitrarily route to the OT subnet. You have to implement strict MMC and IP allow listing so that only dedicated, heavily monitored engineering workstations can even attempt a TCP handshake with the PLC.
Agreed. Securing the perimeter is foundational, but we need to examine the actual mechanics of what happens once they bypass that perimeter. The attackers are leveraging PUGET for unauthorized read and write operations.
Yes. They are targeting the programmable data blocks within the PLC memory. By initiating read commands, they conduct silent reconnaissance. They map the memory structure to understand exactly how the physical process functions.
Figuring out what does what.
Exactly. And by initiating write commands using the PUT function, they are actively pre-positioning for disruptive attacks. They can silently alter operating parameters without ever tripping an alarm on the operator's screen.
Well, here is where I strongly dispute the catastrophic severity you are assigning to PUGET regarding core safety and critical logic.
Why? It's direct memory access.
Yes, but we need to look at how robust industrial systems are actually architected. Competent OT engineers absolutely do not use PUGET for transferring large amounts of critical process data or safety interlocks.
Okay, but they still use it.
They use it for basic polling. PUGET is a unilateral communication method. The client reaches in and reads or writes, and the server, meaning the target PLC, is entirely passive.
Right, the OS handles it?
Exactly. The target controller's operating system handles the requests in the background, meaning the application logic doesn't even know the memory just changed. That is a terrible design pattern for reliability. Real engineers use BSEND and BRCV instructions.
Okay, function blocks 12 and 13.
Right. Specifically, function blocks 12 and 13.
But how does using a different function block inherently mitigate an attacker who already has network access to the controller? I mean, they are already in.
Because BSN and BRCV fundamentally require bilateral active configuration. It relies on a client-to-client principle. You have to explicitly program the connection on both the sending and receiving controllers.
Right.
You assign a local ID, a connection ID, and a cryptographically paired RID. You define exactly what data block is being transmitted. For instance, passing up to 892 bytes from DB2, like a send data block, on the first machine, directly into DB1, a rec data block, on the second.
It's predefined.
Yes. Both PLCs must actively execute their respective function blocks during their scan cycles. Think of Pager A like a stranger walking past a public bulletin board and pinning a sticky note to it.
Okay.
The board itself has no awareness the note was added. BSN and BRCV, on the other hand, operate like a certified bank transfer.
I see.
Both the sending and receiving institutions must explicitly authenticate, expect the transaction, and verify the ledger before a single byte of data is accepted. So an attacker armed with an AI script cannot just arbitrarily inject data into a BRCV block via port 102 if the PLCA's ladder logic isn't explicitly programmed and waiting to receive that specific payload from a verified pre-configured partner.
Okay, the architecture of BSEND and BRCV is certainly more robust for systemic data transfer, I'll grant you that.
Yeah.
But attackers do not require bilateral communication to trigger a disaster.
What do you mean?
They are not trying to gracefully integrate a rogue controller into your plant's complex architecture. They only need to manipulate a single, overlooked, unprotected variable via PUT. Consider an automatic tank gauge, an ATG, in a municipal water facility or a chemical batching plant. If a threat actor uses a PUT command to overwrite the single parameter that defines the high-level overflow alarm, the tank will continuously fill until it ruptures. The PLC does not need to be actively expecting the malicious data. If that single variable was left exposed to PCEE for legacy HMI polling, the attacker alters it, bypasses the core logic, and causes a catastrophic physical incident.
Okay, I concede that a single parameter manipulation can be devastating. You do not need to rewrite the complex application binary or reverse engineer the entire compiled ladder logic to cause physical harm.
Exactly.
Changing a single offset parameter via PGET is like altering the calibration on a robotic arm's trajectory by just a few degrees.
Right.
The core motion program remains entirely untouched and looks perfectly healthy to the engineer, but that tiny offset causes the robot to slam into a safety cage at full speed.
Yes. And the consequence of this technical reality means defenders cannot sleep soundly just because their core plant architecture relies on BSN and BRCV. Security teams must actively monitor for unauthorized PUT share operations, particularly looking for writes happening outside of approved engineering change windows.
Right.
The CCA advisory points defenders toward hunting for snap7.dl signatures, or anomalous Python execution on the network, specifically originating from machines that are not cataloged as approved engineering workstations.
Operational decisions.
With the mechanism clear, let's turn to the operational decisions.
So we have to translate these low-level memory mechanisms into actual business risk. When an attacker secures read-write access to a PLC, we are staring down the barrel of severe disruption to critical industrial processes.
Bad.
It translates immediately to halted production throughput, compromised product quality, or in the case of the water sector, the contamination of public utilities. We are evaluating massive equipment damage and cascading failures across interconnected supply chains.
Right, so consider the operational decisions sitting on the plant manager's desk. Your security team is monitoring the network, and they detect unauthorized S7 comm traffic.
Okay.
They see sequential IP scanning on the OT subnet, or they flag an unauthorized block read that matches the footprint of a Python script. What is the immediate operational order?
Well, seeing unauthorized traffic, actively probing industrial controllers, mandates an immediate operational response. The decision must be to isolate or completely shut down the affected PLCs.
Wait, shut them down?
Yes. You have to sever the connection or stop the physical line to prevent a logic hack from executing. If an attacker is successfully reading memory blocks, they are actively calculating the offsets required to write malicious data. Allowing the process to continue running while they pre-position for a disruptive attack is just negligent.
I fiercely dispute the idea of hitting the emergency stop based on network reconnaissance.
Why? You have to protect the equipment.
Shutting down a critical automotive manufacturing line, or worse, cutting power to a municipal water pumping station based on suspected network scanning, sets an incredibly dangerous and unsustainable precedent.
But the risk.
Shutting down the plant every time an IT security tool detects an anomalous ping on port 102 guarantees 100% downtime. That is literally burning down your house because you saw someone looking through the window.
That's a bit of an exaggeration.
It's not. You are executing the attacker's primary objective on their behalf. A suspected network intrusion does not legally or operationally justify halting physical production. Furthermore, the assumption that we can just blanket the OT network with IT security tools to get better visibility and justify these shutdowns is deeply flawed.
Visibility is how you prevent the damage.
But legacy industrial controllers, like an older S7 running a critical turbine, for instance, simply cannot handle the jitter and CPU overhead of an active real-time security agent constantly pulling it for status updates. You will crash the PLC and drop the turbine just trying to monitor it.
Okay, but focusing exclusively on the financial cost of operational downtime ignores the exponential cost of physical destruction.
I'm not ignoring it, I'm just balancing it.
Look at the recent water sector compromises, or CISA's explicit warnings regarding equipment damage. If an attacker leverages PEGT to silently force heavy equipment outside of its engineered design parameters.
Like overpressurizing a pipe.
Exactly, intentionally overpressurizing a pipeline, or overriding the thermal limit on a generator. The resulting physical destruction costs millions of dollars and takes months to replace. You cannot allow a critical physical process to continue running blind when you have definitive proof that an AI-driven script is actively mapping the controller's memory structure.
Look, I will qualify that uncontained physical damage is undeniably the nightmare scenario. A destroyed turbine rotor takes 18 months to replace, whereas a paused turbine can be restarted in 4 hours.
Exactly my point.
However, the cybersecurity department cannot own the shutdown authority on a factory floor. Production management owns quality and uptime. Cybersecurity's mandate is to provide irrefutable evidence of unauthorized change. You cannot halt physical reality based purely on a network anomaly. You need proof of a compromised physical state.
That tension points us toward a critical consequence then. The operational decision must heavily balance preserving production with verifying physical reality. We have to separate the concept of software integrity from the observation of physical output.
And evaluating that evidence loop is where most security frameworks fail in OT. To avoid triggering catastrophic and unnecessary plant shutdowns, plant managers need absolute proof of what the attacker is actually doing.
Right, and providing that proof requires real-time telemetry from the industrial controller. Security teams need to know exactly what the attacker altered the millisecond it happens.
This is hard to get safely.
But if a rogue PUT command traverses the network, defenders need a system that instantly identifies which data block was modified and what the new value is. The CISA advisory specifically recommends deploying ICS-aware intrusion detection systems.
Specialized IDS tools.
Yes, technologies built by vendors like Clarity, Dragos, or Nozomi. The guide is to monitor all S7com traffic traversing TCP port 102, establish a baseline for legitimate engineering behavior, and configure alerts for any deviations.
But here's the reality check on that. Deploying real-time telemetry fundamentally introduces latency.
But only a tiny bit.
A tiny bit is too much in OT. If an IT team deploys an active ICS-aware intrusion detection system that begins constantly polling a legacy S7 300 or even a heavily loaded older S7 1500 to check its memory state, they risk overwhelming the communications processor.
The backplane can usually handle it if configured right.
These controllers govern physical machinery by operating on incredibly strict deterministic cycle times. If a security polling request delays the update of a critical output valve by just a few milliseconds, it introduces mechanical jitter into the physical process.
Okay, but rejecting monitoring entirely leaves defenders completely blind. We cannot simply wait for a mechanical failure to alert us to a breach.
Network-level passive monitoring is acceptable.
Passive monitoring.
Yes, using a span port on an industrial switch to passively copy traffic on port 102 without interacting with the PLC is a standard practice. But active on-device polling, where a security tool is actively querying the PLC, must be strictly justified by evaluating the consequence of a failure against the measured CPU overhead on that specific controller.
Right.
You cannot just drop heavy IT-style monitoring agents into a fragile OT environment and expect the physics to just adapt.
Okay, I hear the engineering constraint there. The consequence is that security teams must baseline legitimate behavior passively first. Defenders must rely on deep packet inspection at the switch level rather than actively querying the controllers and hoping the CPU doesn't fault under the pressure.
Pressure test.
That sounds reasonable in principle, but now let's put it under real constraints with the pressure test.
Okay, let's play this out. Consider this scenario. You are managing a critical infrastructure facility. A strict regulatory clock is ticking, meaning you have legally mandated uptime requirements.
Okay, so I can't just stop.
Right. Your passive network monitoring flags definitive evidence of reconnaissance on your OT subnet. A Python script exhibiting specific Python snap 7 S7com formatting was detected executing on a compromised engineering workstation.
Bad news.
But you cannot stop production. You are under immense pressure to secure the system against AI-driven manipulation while the physical machinery continues to operate at full capacity.
So we have an active threat actor inside the perimeter, the capability for rapid AI-driven parameter manipulation, and an absolute mandate to keep the production line moving. What is the tactical move?
The tactical move is to retreat to the heart of the safety system. To guarantee safety against an attacker capable of rapidly iterating exploits against the standard logic, defenders must embed specific cyber checks directly into the safety program, the F program, of the fail-safe controllers.
Inside the F program.
Yes, we need to construct logic inside the impenetrable safety envelope that mathematically validates the parameters being sent from the standard user program before the physical machine is allowed to act on them.
I have to shut that approach down completely.
Why?
Yeah.
It's the most secure area of the controller.
Referencing the official Siemens safety programming guideline, engineers absolutely cannot stop, modify, or alter the F program on a whim to address a cyber threat.
Not even to add a security check.
No, the F program is independently validated by third-party safety assessors. Any change made to the safety program inherently alters the collective FSW signature.
Okay, but what exactly is the software signature governing here?
The F signatures are cryptographic checksums used for the unambiguous identification of the safety-oriented program. Altering an F program isn't like pushing an update to a smartphone app.
Right.
It's like changing the structural blueprints of a skyscraper while people are already working inside it. The moment you erase or add a single line of code to insert a cyber check, the mathematical signature breaks. Your safety compliance shatters.
Oh, I see.
It requires a full reassessment, external validation, and a completely new equivalence test. Furthermore, feeding non-safe standard inputs directly into a safety program is a critical engineering violation.
Because of data corruption.
Exactly.
Right.
If the standard user program, which we assume the attacker has compromised, writes corrupted data precisely while the safety program is attempting to read it, it causes data corruption. The safety system's cyclical checksums will fail immediately, and the CPU will trigger an FSTOP.
And that halts everything.
The entire controller halts. By trying to secure the safety logic, you just cause the exact catastrophic downtime you are mandated to prevent.
Well, leaving the safety logic untouched creates an unacceptable blind spot. If the compromised standard user program is allowed to modify fail-safe data, it bypasses the safety mechanism entirely.
Yes, if poorly designed.
The attacker manipulates the standard HMI to overwrite the critical safety thresholds, and the F program just accepts it. Leaving the safety logic blind to the broader system state is an invitation to disaster.
Which is why Siemens Engineering provides a very specific, strict workaround for data exchange between the standard user program and the safety program.
How do they handle it?
You must utilize a preprocessor.
Right.
You copy the required data from the standard program, like in a standard data block, let's name data to safety, and you move it into a dedicated fail-safe data block, data to safety F.
So it's buffered.
Yes. This is executed using a standard MAVI statement at the very beginning of the controller's stand cycle, explicitly before the F runtime group executes. This architecture ensures that the F program reads only protected, static data during its critical cycle. The standard program cannot corrupt the data mid-cycle.
Ah, okay. That architecture preserves the boundary between compromised IT data and physical safety.
Exactly, and as a consequence, we preserve the independently validated safety functions and operational boundaries. Cybersecurity controls must never compromise safety compliance. Attempting to embed untested, experimental cyber checks into validated F logic violates the core principles of industrial safety.
Right. But if modifying the safety logic to add cyber checks is off the table and deploying heavy network telemetry on the device itself threatens to crash legacy controllers, we are essentially flying blind at the execution level.
We aren't, though.
We are facing threat actors leveraging AI to rapidly iterate and tweak physical parameters, and we have stripped away our visibility into the controller's immediate actions.
We are absolutely not blind. We pivot to using production evidence. This is the fundamental reality of how operational technology works.
What do you mean by production evidence?
Instead of demanding plant-wide, real-time IT telemetry from the PLCs themselves, we shift our monitoring to the downstream physical outputs. We monitor the mechanical torque on the robot joints.
Okay.
We evaluate the data from the optical metrology scanners. We rely on the vision systems and the automated quality gates at the end of the line. We compare the actual physical motion and the geometry of the final product against a known good reference model.
Let me process the implications of that strategy. You are suggesting that if an AI-generated script successfully utilizes GGAA to silently change a motor speed parameter or a positional offset deep in the controller's memory.
Precisely.
And even if our passive network sensors completely miss the malicious S7 COM packet traversing the switch, the physical machine will mechanically move differently.
Yes, it has to.
So the downstream quality inspection, like a vision system checking the integrity of a weld, or a torque sensor monitoring the mechanical resistance of a valve, will catch the physical drift. We detect the cyber attack by observing the physics of the plant.
Yes, production owns quality. If the physical quality drifts out of tolerance, we know definitively that something changed. The engineering team then investigates to determine if it was a mechanical degradation or an unauthorized parameter manipulation. The physics never lie.
I can see this point entirely.
Really?
Yeah. Relying on existing downstream physical inspections, torque monitors, the vision systems, the metrology gates, it is vastly more defensible and operationally feasible than attempting to force invasive cyber instrumentation onto delicate fail-safe CPUs.
It just works with the reality of the floor.
It respects the rigid engineering constraints of the factory floor while still providing an irrefutable layer of detection against parameter manipulation.
And as a consequence, our ultimate decision in this pressure test is a major paradigm shift for most security teams. We prioritize monitoring changes to programs, tool data, frames, and recipes by actively reusing physical production evidence.
It's brilliant, honestly.
We only escalate to deploying heavier IT instrumentation on the network when the consequence of a mechanical failure absolutely justifies the residual risk, and we have mathematically proven the legacy hardware can handle the processing overhead.
Makes perfect sense.
Key takeaways.
With the trade-offs on the table, let's bring it all together in the key takeaways.
So the first critical takeaway focuses on the adversary's evolving capabilities. The historical barrier to entry for attacking industrial control systems has completely vanished.
Right?
Artificial intelligence allows threat actors to rapidly iterate and deploy exploits, utilizing open-source tools like the pure Python Snap 7 library. The risk of leaving PLCs exposed to the internet is no longer a theoretical tabletop exercise. It is an active, ongoing threat campaign severely impacting critical infrastructure today.
Right. And the second takeaway dictates that technical defense relies on robust OT architecture rather than simply throwing modern AI detection tools at a crumbling foundation.
You have to build it right.
Exactly. Facilities must rigorously isolate the OT network, disable legacy PA-ET communication if it is not absolutely required for legacy HMI polling, transition to using BSN and BRSysV for secure, configured client-to-client data transfers.
Yes.
And fundamentally, strictly segment standard user programs from safety logic to preserve those critical F signatures and maintain regulatory compliance.
Which brings us to our joint takeaway, which focuses on operating effectively under immense pressure. When the regulatory clock is ticking and the threat is active, rely on physical reality.
Address the physics.
Utilize existing quality gates and physical downstream evidence, like torque resistance and optical metrology, to detect malicious parameter drift. Execute this strategy instead of risking a catastrophic CPU SOP or violating safety compliance by deploying untested IT monitoring tools directly onto fragile industrial controllers.
We have dissected a massive amount of technical and operational friction today, but you have a final provocative thought to leave the audience with.
I do. Consider the trajectory of the threat. We have spent this entire deep dive analyzing how attackers are utilizing AI to write the Python scripts to attack these controllers.
Right, the code generation part.
But if defenders shift their strategy to rely heavily on physical downstream evidence, depending on vision systems and torque anomaly detection to catch the drift, we must look ahead at the adversary's next move.
What's next?
How long until threat actors utilize AI not simply to write network packets, but to actively model the physical downstream processes in a digital twin?
Oh, wow.
How long until the AI calculates exactly how to manipulate the parameters so that the physical destruction occurs without ever triggering the torque sensors or the vision system anomaly detection thresholds?
AI is not the main security problem in the current Siemens S7 campaign.
Cybersecurity under pressure, real attacks, real lessons.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared. Stay critical. And keep following the evidence.